Hello everyone and welcome to our presentation on software process modeling. We are Team Electra and we hope you enjoy this presentation. Our team is composed of 4 team members, Luis Dominguez, Bo Wu, Torrance Leung, and myself, Alexandre Alaba, who are going to walk you through the different topics that we're going to cover in this presentation. The first thing that we must understand before actually going into the different models that we will be talking about is what is a process, like what are the characteristics of a process. So in terms of software engineering, a process or a main process will prescribe all major process activities. It will produce intermediate and final products, which means that you are constantly going to be able to picture out what is it that you want to deliver, and along your intermediate steps, you're going to be able to picture what is the how is the product that you want to deliver looking at the moment, and that way you're able to perform changes and all the required modifications in order to reach the final product that you desire or your customer desires. As we see on the right, it may be composed of sub-processes with hierarchy or links. We can safely assume that any process that is on the top has a higher hierarchy than the ones in the bottom. And you can see that we begin from one main thing and then end up at the bottom with only one final goal, which could be, in the best case, the final product that we are expecting to deliver. As anything in life, and a concept that's very common to us as software engineers, is that any major activity, any major process has entry and exit criteria. When we build our programming, when we build our programs, we're always thinking about inputs and outputs that are required in order to perform an efficient software development. So in this case, we're going to generalize and go into more of entry and exit criteria that you need to understand before actually diving into the process itself. And in order to make it easier, we can also think that processes are organized in sequence, so timing is clear. We know what step, what is the order in which one of the steps or the instructions, and we know what goes before and what goes after. So there's 4 major activities that we want to discuss about software process. First of all, you got software specification, which is pretty straightforward. It's just comprises the main functionalities of the software, and then constraints. The constraints are on them. It's really important to point out that almost everything that we do in this life, specifically in software engineering, is going to have some constraints, some boundaries that we have to limit ourselves to, and this is not the exception. The next thing would be software design and implementation, which is also pretty straightforward. It's just understanding the software has to be designed before it has to be programmed, and then it has to be programmed. So those are the 2 basic building blocks of any software process major development. After that, we need to consider the software verification and validation, which it's just thinking that the software must conform to specifications that meet customer requirements. And finally, once you have finished, tested, specified, designed, implemented all your software parts, you must be able to maintain it, which is basically being able to constantly modify it in order to meet all the customer and the market requirements a long time. If you're not able to successfully maintain your code, meaning that you're not able to evolve with the market and the customer needs and the constant requirements from your customers themselves, your software is probably going to be taken out of the market. One distinction that we must make is there's 2 different approaches at software development. The first one is a prescriptive approach, which asks the question, how should software be developed? It's more looking into the future. It's more about understanding what mistakes are being done now, what errors, what things could be improved on, and thinking about the future. So it is mainly comprised on defining how the process should be enacted in relationship to its features. And on the other side, we have the descriptive model, which asks the question, how is software now developed? So it is mainly concerned about specifying a process now, which in most cases will be used within an organization, or basically concerned about representing a process or a proposed process to predict some process features. So now that we've talked a little bit more about process, we need to understand what a model is. Like, what are we need to be able to picture out why do we want to model stuff? Like, what is the value behind all this? Why don't we just build our software and deliver it and forget about everything else? The first thing is that we can understand that modeling makes things simpler, brings things to a common language in order to form a common understanding. across different stakeholders. So people from across different platforms, different language users, different school, like different like old school developers against agile developers, the technical people against the business people. They all have to be able to understand what is the process that we want to achieve. So that's one of the biggest reasons why we model stuff. Also, through modeling, we can easily find inconsistencies, redundancies, and omissions, or any other thing that must be fixed. So this is going to help us achieve all these changes and fixes at the beginning or during the software process, or the process in general, instead of at the end. It is also helps us to find and evaluate appropriate activities for reaching the process goals, what is going to take us there faster and how, and also to tailor a general process for a particular situation in which it will be used. The first model that we're going to talk about now, it is the waterfall model, which is not much more than just the linear sequential design process, where any single process flows largely in one direction. Like we can see in the picture, water begins from the top and it falls down to ground level. So it is the understanding that it has to go through all the phases. It has to go through conception, initiation, analysis, design, construction, testing, and of course the deployment and maintenance. And that no one of these phases could be skipped in order to reach the second one or the next one. Water, when it comes from the top to the ground, it goes through the whole space defined for that waterfall. It's not like water is at the top and then it suddenly appears down at the bottom. It has to go through every single one of the steps. So this model has both pros and cons. On the side of the pros, we know that it is a systematic method, so it's gonna be easy to picture or to visualize the different mechanisms that must be approached in order to complete this process. It is also easy to follow. So for someone who's seeing this the first time, or like we mentioned before, there's a great way of simplifying stuff. So it's easy to follow the steps and it turns any task into a mechanic set of instructions. Since we know that A goes before B, before C, before D, and then we deliver the product. So it's not much more than just following a set of instructions, and then of course later on, each one of the developers can add their own personal taste to whatever they're developing, but they all fall into the same backbone of the mechanic set of instructions. And of course, we are always working on incremental development, so we're not just trying to solve one whole problem at once or deliver a product instantly. We are going step by step and adding into the product that we're currently trying to develop. On the other hand, on the cons, we have no guidance on changes. This model also views software development as manufacturing, which could be dangerous because if you have ever coded anything in your life, or if you ever worked in a software engineering company, you know that software development is a very back and forth process. It's not just linear. It's not like you put a piece of metal at the beginning and then it goes through a bunch of different heating or molding or any kind of processes, and then at the end you get your product. There's going to be a lot of putting effort in and out into different aspects, going back and forth, going to step one, step four, then two, three, one. So this is very dangerous when we're talking about software process. And of course, since you're only able to see, you're working in an incremental fashion. In order to have the complete product, you have to wait for a long time before the final product is actually delivered. So this is a better picture, a more simplified picture of the waterfall model. Of course, there's many things that can go in between these phases, but the main things we see here is how everything begins at the top and it just flows down as the water flows down from the beginning, the requirements, all the way down to the maintenance. In reality, like I was mentioning before, software engineering is not a linear process. Software engineering or software development is more like we can see in this image. It is a really complicated process when you go back and forth between different stages without actually paying attention to a specific order. Of course, you're always going to be based on your backbone when you want to begin with your requirements and all the specifications before you test and maintain your code, or you gotta build your code before you test it. So those things are very obvious that they have to follow a sequence of steps. But once you have done at least your first iteration, then you're gonna fall a lot into the back and forth style that I was talking about before. There's a small modification to a waterfall model, which brings us to the same, pretty much the same model, but now with a prototype added. So a prototype is not more than just a partially developed product that is utilized along the design and development process to visualize what has been conceptualized and catch error in the early stages of development, or decide on any required changes or fixes that have to be done. This brings us to two questions while we're seeing our prototype. Once we have our prototype in our hand, we need to be able to validate and verify what we're trying to achieve. So on the validation side, we have to ask ourselves if all the requirements have been implemented, if they have been implemented, and then on verification, we have to figure out if all the requirements have been implemented correctly and with high quality. This is more or less how the waterfall model with a prototype would look. It's pretty similar to the one before, except that we now add the prototype into the picture, and we see how it goes back and forth within all the different stages of the software engineering process.
A slight variation of the waterfall model is the V model. The main difference between the two is that the V model allows us to go back to previous stages during the testing phases, also known as V&V, verification and validation. This is the main focus of this model. After the requirement analysis, the system design, the program design, and the actual coding, then the testing phase begins. Unit testing is performed to verify the design of the program. Then integration testing helps verify the integrity of the architectural design of the program. Finally, acceptance testing is what determines whether the system requirements were met. If any problems are found during the testing phase, we can simply go back and re-execute the left-side steps as necessary. Next up, we have the prototyping model. Prototyping allows us for a repeated investigation of the requirements for the system of the specification. It allows for a constant analysis of the requirements for the system that is being developed alongside the customer. This method of development reduces the risk and uncertainty during the development process, given the constant customer involvement. Given some initial requirements, the team comes up with a design which is transformed into a prototype. This prototype is then evaluated by the customer. If the prototype does not fulfill the customer needs, this prototype goes into review and is updated accordingly in order to come up with a new design, starting this cycle over again. If the customer is actually satisfied with the design, then this final developed prototype is developed as the final product, and then it is tested, which in reality could bring the project back to the customer feedback loop in case V&V do not provide satisfactory results. Up next, we have the operational specification model. In this model, requirements are examined alongside the implications they bring to the table in a very early stage of development. This allows for the functionality and the design aspect to merge together during the upcoming development stages. The original requirements for the system, which can be informal or incomplete, are examined and revised extensively when trying to design the operational specification of the system. Once these requirements are as clear as possible, only then the implementation stage begins for the specification. This transformed specification is then tested before delivery. If V&B determines that the specification does not satisfy the requirements of the customer or by the design itself, then we go back to the design stages of the operational specification. The transformational model cuts some steps present in other models by applying a series of transformations onto a specification to turn it into a deliverable system. These transformations can be of different types, such as ways data is represented, which algorithms are used in the implementation, the optimization of the system being worked on, and the compilation of the system. This model relies on an initial form of specification of the system on which the previously mentioned transformations may be applied. First, a formal specification is produced which is compared against the requirements of the system to make sure it satisfies it. Then, this original specification undergoes several transformations before going into testing to develop the most optimal system. These transformations should go onto a formal development record on which the transformations made, the order in their sequence, and the rationale behind them are documented. Phase development is another model that may be followed by software development, in which software is delivered in periodical instances. Some of the advantages of phase development come in the form of modularity. Since each part of the software is released individually, it is easy for the development team to focus on a specific area of skill on each release. Similarly, frequent releases allows developers to fix unexpected bugs globally relatively fast. Also, on the customer side, training can begin as early as the incomplete system is made available, even though all model functions may be implemented at that stage.
There are some advantages about using these two models, and the next slide is showing the graph which illustrates how them works. So the first one, incremental development, is generally at the very beginning you have probably a prototype of how your software is gonna look like, and it's functional. And I mean, in very short time, your users can start to use it. But after that, we're gonna add more and more features, more and more functions into that. The iterative development is pretty similar, but the difference is that uh, after each iteration, some parts, some subsystems will be replaced. This model, the spiral model, was suggested by Barry Boehm in 1988. He suggested this model because he was thinking that the traditional waterfall model, which was introduced by Alex, my teammate, on Tuesday, was just too. I mean, what if some risks happen during one of the during the building of one of the subsystems of the whole waterfall process? You never know what's gonna happen, right? So he suggested this spiral model. The graph for the spiral model basically looks like a spiral, and that's also why this model gets its name. Uh, this model takes the cues from the iterative model, but the difference is that they added the risk analysis into each iteration. So, and another difference is after the very beginning iterations, probably the first and the second one, they're probably just a very simple prototype, but not functional at all. So yeah, and after so many iterations, the software will be done. There's some disadvantages. The first one I think is they don't. It's gonna take a long time to build the whole software. The next thing I'm gonna talk about is actually a methodology which is called agile methods. Uh, Below is the four principles how the agile methods works. Value individuals and interactions over process and tools. Invest time in producing working software, not in comprehensive documentations. Focus on customer collaboration, not contract negotiation. Always respond to changes, not always follow the plan. So about this agile methodology, I want to talk about some software engineering background. So this method has already been around there for probably more than 10 years. And we all know that software development is a highly competitive uh, industry. So let's think about this. If a customer or a company just want to build a software, and there are two software companies which will build this software for them. One of them says, "Oh, you're not gonna get this software in 2 years because it's gonna take a long time to build the whole software." But another just tell you that, "Oh, you can just start to use it in maybe several months, even several weeks." Uh, but you are just gonna get very simple functionalities, and we're gonna add more and more and more into that. So which one you're gonna choose? Obviously, you're gonna choose the second one. The first one is gonna lose their business most likely, right? That's why this agile methods is very popular in nowadays software industry. Here are the four most classic agile processes. The first one is called extreme programming. The second one, Crystal. The third one, Scrum. The final one, adaptive software development. I want to focus on the first one, the third one. The first one, extreme programming. Here you can see here. It's the 12 phases of extreme programming. So I think the best environment for extreme programming is gonna be the whole development team. Obviously not gonna too big, probably 10 or 15 persons, and also including the customer. Yeah, the customer is also part of the development team, and they just work every day in the same office, maybe and with a comfortable environment, and the every morning they have a like probably 50 minutes meeting and talk about everything and make sure everything is okay, and they start working. And this is very effective because you see there's a pair programming. Basically, people are divided into teams, and every team contains more than two people, 2 to 3 people. Uh, so when they working, they are always gonna talk with each other to make sure everything is all right. So it's very effective, and in a very short period, you can get the very first release, and you can just start to use it. Yeah, this is the whole structure of the extreme programming, which contains many iterations. The longest one is gonna take months. Uh, it's gonna be the release plan, but that's already the longest one in the whole iteration, and there are many sub iterations. I mean, you can see the smallest one is pair programming. It's the unit is in seconds because they are always communicating with each other, right? Yeah, this is the Scrum. Scrum basically uh, the whole team working in sprints. So every sprint generally lasts between 2 to 4 weeks, and after each sprint, they're gonna have a group meeting and talk about the what they're gonna do during the next sprint and what they have done, what they already have, and make the whole group to go toward the same direction, same goal.
Now we're going to look at notation. Notation in process modeling is used to precisely define whatever it is that the process wants to do. This type of notation may be textual, graphical, or perhaps a combination of those two. This helps to focus the process because the process model, as it stands, is merely a high-level view of the process. The static model uses a paradigm where people perform roles while resources perform activities, leading to the production of artifacts. This is a complicated way of saying that the static model simply takes inputs and transforms them into outputs. Within the static model, there are 7 parts that we need to pay attention to. Activity, which is something that happens in the process. Sequence, which is the order of activities. The process model, which means that you can have parts of the process with its own sub-process, and this can happen recursively, go down as far as you wish to any level of detail that you need. Resources, which is something that is necessary towards the process. It could be a person, a tool, anything that is necessary to complete the process, it can be considered a resource. Control, which is some external influence on process execution. It could be a mechanical control, electronic control, human control. It's simply some external force that applies some influence on how you would otherwise execute the process. Policy could be something like the agile methods, the scrum methods, or the extreme programming methods. These are things that you use to guide how the process is executed. And lastly, we have organization, which is hierarchical structure of process agents, basically the people that carry out the process. And you can group these into physical groups, logical groups, and related groups. Dynamic models enact the process. This allows the users of the model to visualize how the process's products change over time. This allows us to simulate the process and refine it before committing resources towards it. Line notation is a type of static modeling. It is centered around templates and forms to capture the particular details of processes. Templates can define one of 7 things: relationships, process states, operations, analysis, actions, roles, and artifacts. Out of these, artifacts are what you would consider the outputs of whatever you are trying to create. Operations, process states, relationships, analysis, actions, and roles are pretty much what you would expect from their names. Many layers of abstraction are used to describe the process model within line notation, and this is a way of saying that you can go use these forms for any amount of detail within the process model that you require. Graphical diagrams or transition diagrams supplement the model, and this shows how states are related to one another. This particular diagram is a process state diagram example. What we have here is an example diagram of a car starting up. The boxes that are outside the larger boxes, so for example, car engine driver above initiate, are the entry conditions or entry states of certain artifacts within the system. And then going across from that box, you have on, in-car, drive, stand, and that connects to the rightmost part of that smaller box: car engine, driver, car gear, and car speed. These are the exit conditions or exit states, and these go and they transfer control over to park, and it shows how the artifacts, conditions, or states are related to one another within a system. Dynamic modeling models productivity as activities occur. Arrows indicate how changes in one factor affect changes in another. Some example relationships and how they affect productivity could be: increasing staff size would cause an increase in communication overhead. Or if you're planning to bring on more hires, the closer the product is to completion, the longer the new staff needs to learn about the project before they become productive and contribute towards the project. Another one would be how schedule pressure versus workload tolerance of the developers can hinder the productivity of the individual. Marvel specification language is a part of practical process modeling. Marvel specification language has 3 primary constructs. Those are classes, rules by which the classes operate by, and tool envelopes, which allow interfacing between the model process and the classes within the process and how they should interact with the actual process. This allows researchers to run instance simulations and collect results for different scenarios. This is an example of Marvel specification language. This shows the class, ticket, and the rules for diagnosing ticket within the sub-processes that we saw on the previous slide.
Well, that is pretty much what we have for you guys today. Thank you very much for your attention. We hope you were able to understand and get some new knowledge related to the software process models. Thanks again.